in listen-only mode.
Hello, welcome to this SOFinar on volume meshing features in SOFiMSHA. My name is Yorgos Balafas and I'm working in the research and development team of SOFiSTiK. Today's topic is on volume modeling using SOFiSTiK with emphasis on features recently introduced in our latest major release, SOFiSTiK 2016. Before getting started, I would like us to take a few minutes in order to get familiar with the volume modeling workflow and the tools we're going to be using. SOFiMSHA is a module that works mainly on a finite element level. For simple structures, it is enough if we start modeling directly within SOFiMSHA. However, depending on the complexity and the geometry of the structure, it is often required that a structural model is generated beforehand. For this purpose, we can use SOFiMSHA either as a standalone module, or combined with one of the provided graphical user interfaces, such as SOFiPlus or the SOFiSTiK Rhinoceros interface. The commands we provide for volume meshing are the following, here illustrated with blue color, those commands that have been added in SOFiSTiK 2016. For unstructured meshing, we can use the SVO command in SOFiMSHA or UMesh command along with UBound command in SOFiMSHA. This will result into a tetrahedral mesh. For structured meshing using hexahedral elements, we can use the trunk command or the brick command in SOFiMSHA, as well as the recently added extrusion and lofting commands. Finally, we're going to take a look into generating interfaces between volumes. Even this is not a procedure that results into volume elements themselves, it's often required that we generate an interface between volumetric regions, and for this reason we can use the spree command or the interface command in SOFiMSHA. Let us take a closer look to these commands briefly before we go to some examples. UMesh command is used combined with UBound command for generating unstructured meshes. It is similar to the SVO command that many of you may be familiar from SOFiMSHA. The idea is that we use UMesh in order to define the meshing parameters of the volume that we want to mesh, and afterwards we need to use the UBound command in order to define the boundaries of this volume. Therefore, these two commands must be combined, used one after another, and we have provided the possibility to define both outer boundaries, defining the volume, or even inner boundaries in case this volume contains internal voids. We have also provided some auto-detection boundary algorithms for SOFiMSHA. Going to trunk command, this is a generic transformations command in SOFiMSHA. One of the possibilities that this command offers is the extrusion along a direction or an edge in a way similar to the command illustrated here. In a similar manner, we have included a dedicated extrusion command in SOFiSTiK 2016, which can also generate elements of a higher order. We can select some source elements and define an extrusion direction or an extrusion path along an edge or a structural line. and generate elements of a higher dimension, or even generate layers of spring elements or support conditions. There is available the brick command, which is able to generate structured meshes as long as the volume is a cuboid, meaning that it can be defined by 8 nodes at the corners of the volume. We have also added a Lofting command in 2016, which is able to interpolate layers of brick elements between a source and a target area. There is the possibility to define guiding curves at the boundaries so that we can have some curved boundaries, for example. And the condition in order to use lofting is that the source and the target areas must be meshed with a similar mesh. And by similar in this context, I mean a topologically equal mesh. This can be achieved in SOFiMSHA by making a reference to another area. When we define our target area, we make a reference to our source area in a syntax similar to this one illustrated here. If we are working entirely in SOFiMSHA, we could simply copy the quad elements that we consider to be source elements to another position that we consider it to be a target area. Finally, for generating interfaces, we have 2 possibilities. Either using the spray command. In this case, we need to model our volumes with a small distance in between. Afterwards, we can select quad elements existing on one volume and quad elements existing on the other volume and generate spring elements in between using a syntax similar to this one. Here we have selected quad elements from group number 1, and we have asked SOFiMSHA to generate spring elements to connect these quad elements with group number 2, quad elements of group number 2. We have also added an interface command which works a bit differently. In this case, we do not need to generate a small gap in advance. However, we select a structural area where the interface we want to be generated. Here it is illustrated in orange color. And as shown in this command, we have, for example, selected structural area number 1, providing a plus or a minus sign in order to select at which side of the structural area we want the interface to be generated. And afterwards, SOFiMSHA will detect all brick elements that are connected to this structural area, decouple them from the structural area, and introduce spring elements in between. If we want, we can also introduce a small gap for visualization purposes and checking the connectivity of the resulting mesh. We have seen the main tools that allow us for volume meshing using SOFiMSHA. And now I would like us to see a few examples using these commands. The first example we're going to use is a tunnel intersection. For this example, we're going to be using lofting, extrusion, and interfaces. Today, I'm going to use the SOFiSTiK Rhinoceros interface in order to generate a structural model, which I will afterwards export and start the volume modeling in SOFiMSHA. However, you're free to select your favorite way of generating a structural model, for example, SOFiPlus. More details on how to use the graphical user interfaces can be found in the SOFiSTiK documentation. Now, let's first describe our initial model. This is a pure rhinoceros model without any structural elements so far. What I have done here is I have generated two structural areas, two lines, which I have swept along a curved path. Followingly, I have generated an area which I have extruded to a solid. I have done this for the only reason in order to find the intersection points of this solid with the previously generated areas. Now I'm going to hide these parts of the model that are no longer necessary, and I'm left with this part. Additionally, I have generated some curves that will serve as guiding curves for lofting or paths for extruding elements. Let us first generate some volume elements in between these two areas. First of all, I'm going to make these structural areas. This is structural area number 1001, using the SOFiSTiK Rhinoceros interface, and this is structural area 1002. Now, as we said, in order to be able to loft between these two areas, we need to make sure that the meshes of these areas are similar. We can do this afterwards using SOFiMSHA, but since the Rhinoceros interface provides us with an advanced field here at the bottom of the interface dialog, I can use this to reference one structural area to another. So here I have selected structural area number 1002, and I will couple it with structural area 1001. I'm entering manually SARS command with reference type structural area and reference number 1001. Let us first try to export this model and see the results. Let's create a TEDdy project. For this example, I'm going to do it step by step in an interactive mode, going back and forth from the structure model to the finite element model. We will do this in order to have a better overview of what is going on, and also to see some issues that may come up, what is the reason behind them, and what solutions there are. So we're going to pay attention to the warning or error messages that SOFiSTiK will provide, the SOFiSTiK models. Let's run the example. We already have some warnings that we have not defined a material for the structural regions, so let us define a material. At this point, the material is not that important. Let's also make the thickness of these structural areas 0, just for better visualization. Let's try this once again. And we can see that the two structural areas have been generated with meshes topologically equal. Now, let's try to generate volume elements in between. We will open TEDdy. First of all, let's increase the group divisor so that We do not have any errors because of this. And before starting a lofting operation, I would like to generate a structural line here at this point. Before lofting, we need to specify how many subdivisions we want to have in between these structural areas. But instead of providing this information manually in SOFiMSHA, I'm going to generate a structural line that is connected to these structural areas, and the lofting procedure will follow this line as a guiding curve, meaning that it will also follow the subdivision of this line. So I'm going to export this model once again. And now I will start lofting. I'm entering a new task. Restarting the system. And as we said, we want to loft between structural areas 1001 and 1002. Now let us see one issue that may come up in this case. I'm trying to run the model, and SOFiMSHA has failed, saying that there is an invalid number of subdivisions. And the reason is that SOFiMSHA warns us that structural line 1001 has been removed because it's not connected entirely with the model, and suggests that we use control del N0 in order to keep this structural line in the model. So this time structural line 1001 should remain in the model, and SOFiMSHA should be able to detect it. So this is our model after the first lofting operation. We can see the brick elements that have been generated between the source and the target surface. Now let us do the same for the remaining model. This time we will do things a bit faster. Now we want to loft between these two areas, and we also want to loft between these two areas. Let us make them all structural areas first. This is a structural area. Structural area 1004. One more. Let's set thickness to 0 and a material. And we'll follow the same procedure with guiding curves. Now I have also generated here a curve that I want to use as a guiding curve, but we want to make sure that the subdivision is the same as the subdivision of the previously defined structural line. What we're going to do then is we are going to reference this structural line 1001 here in the advanced dialog field of structural line 1002. We're typing SLN S reference 1001. Now in the exported system, these structural lines should have the same number of subdivisions. Let us try to mesh this part first. Let's also assign some group number to the generated brick elements and some material number. Let's generate some additional materials. At this point, we're not going to give much attention to the materials themselves. So we have generated the first part. Let's now generate the second part. Brick properties material number 3, and we want to loft between structural area 1003 and structural area 1004. Let's try this. No topological association could be determined between the source and target regions. Let us check why. Because we have forgotten, of course, to couple these two areas. We need to go here in structural area 1004 and type SARS, reference type SAR, and reference number 1003, which is this area here. Let's export the system once again, and let's try. We can now see this part of the area has been generated, this part of the model with volume has been generated with volume elements. Now we're going to do exactly the same between these two structural areas. Let's reference this area, the target area to the source area, SARS, ref type SAR, reference number 1004. Yes. Now let's make these guiding curves. These are structural lines, and I'm going to select one of them, let's say structural line 1006, and use it as a reference for the other structural lines so that all have the same number of subdivisions. SLNS ref 1006. Now, in this case, we can see that the guiding curves serve for three purposes. One purpose is that it helps the algorithm to make a one-to-one node correspondence between the coupled structural areas. A second purpose of these guiding curves is to define the number of subdivisions, but in this case there's also this curvature on these structural areas, on the structural lines, that will influence the geometry of the final structure. Let us export this system, go to Teddy, define a new group, number 33, material number 4, and let's loft between areas 1004 and 1005. And this is the resulting volume mesh. We can see the influence of the curved structural lines that have been auto-detected. Now, as a final step, we want to generate some quad elements here. We will do that by lofting between this curve and this curve. So let's make these structural curves, lines. We're going to use to reference structural line 1008 when we define structural line 1007. This way they will have the same number of subdivisions, and we're going to loft between these two structural lines because lofting can be also used in 2D cases. This will again serve as a guiding curve. And let's also make this a structural line as we would like us to use it for an extrusion path. Let us export the system once again. Go to TEDdy, group number 21. Now we're generating quad elements. And we want to loft between structural lines 1007 and 1008. Let's try this. We get a warning that there are 21 nodes that have not been used, but this is only because the structural line that we have defined for an extrusion path has not been used yet. So these are the quad elements that have been generated by this lofting operation. Finally, let's extrude these along the path we have defined. Group 34, bring properties, material number 5, extrude, type quad, from group 21 along a path which is a structural line 1009. We can see that the extrusion is complete. However, we can see that the layers of brick elements have been generated parallel to each other. We would like, in this extrusion, to follow the rotation of the structural line that has been used as a path. We're adding then option R, which means rotate, and let's make the thickness of these quad elements 0, and let's try once again. We can now see how the brick elements have been generated following the rotation of the path. Finally, let's generate an interface between these two blocks, the lofted and the extruded one. I'm going to start a new SOFiMSHA task. And I'm going to use the interface command in order to generate spring elements on structural area. We need a structural area in order to be able to generate spring elements. So let's give these quad elements a reference number 21. So structural area number 21, and let's give some spring constant here. We can see the spring elements have been generated at the position we have specified, and the direction we have specified. Let's try to introduce a small gap in order to make this a bit more visible. And let's reverse the side of the structural area or the quad layer in order to generate the interface on the opposite side. We can see that now the spring elements have been generated on the opposite side, and a small gap has been introduced in between these two volume blocks. This gap is optional, and I have just introduced it here for visualization purposes. Now, we have seen how to use lofting, extrusion, and interface. As the last example, it is very brief. We are going to see how we can use UMesh command to generate tetrahedral elements. This is something that is often required when the volume we want to mesh is not possible to be meshed with a structured mesh, or if the resulting hexahedral elements are skewed or of bad quality, then as a last resort we have tetrahedral elements that we can use. Let's open the second example. I will go directly to the generated volume mesh before generating the tetrahedral elements. We will take a look into this. Let us deactivate the quad elements for a moment. So, this is our model representing two tunnels meshed with hexahedral elements, and part of the soil surrounding them also with hexahedral elements. Now, in between, we would like to generate tetrahedral elements to connect these two structures. As we're working in SOFiMSHA on a finite element level, I will be able to define the volume of interest by introducing some quad elements, which I have already generated, illustrated here in this blue area. We're going back to TEDdy. We're defining a group number brick properties for this tetrahedral mesh, and we enter UMesh command, type of element tetrahedral element. We will let at this time the software to define the maximum element size and the progression factor, even though we're able to also manually define it. And afterwards, we need to tell the program what is the boundaries of our volume. I'm using ubound command with one of the auto detection possibilities that have been implemented. Here I will pass the coordinates of a point that I know that is internal to this volume. So I'm choosing coordinates 0, 1, 1 that I know are internal to this volume, and the boundary of this volume should be automatically detected. I'm just running this last part. We can see no warnings. So let's take a look into the structure. Let's deactivate again the quad elements that have served as boundaries for the volume. And we can see here in green the generated brick elements. Let's also make a cut here and show the brick elements, and we can take a look at the volume elements that have been generated. Now, I think I have. Let us get back to our main window. On some technical problems. Just give me a moment, please, to get back to the presentation. Now, I hope that now everyone can see my screen. So these were the two examples that I wanted to present today. You will be able to find further information for these features in SOFiMSHA documentation. The material and the examples we have used today will be included in our next service pack 4 of SOFiSTiK version 2016. Before leaving you, please let me remind you of our upcoming 25th SOFiSTiK seminar, which will be held on the 22nd and 23rd of April later on this year in Munich. We would be glad to see you all there. Please find more information online regarding the program and registration. Thank you for your attention. Please feel free to contact us for your feedback or any questions you may have. And also please make sure you stay tuned for upcoming SOFinars. Until then, happy meshing. Goodbye.